So we'll go ahead and get started. Appreciate everybody for joining here today. We've got a very cool webinar here on optimization and uncertainty and how we map that uncertainty to our optimization and the decisions that we're trying to make. My name's Evan Wimpey. I'll be your host and your moderator. I will talk here for just a couple of minutes and go over some admin, and then I'll introduce our two speakers who are going to take you through an example here on optimizing across uncertainty. So first, a couple of quick admin notes. This is being live streamed. Hi, everybody, live. Also, it's being recorded. You will get a copy of the recording afterwards. And hello, people from the future who are just watching this recording. For the folks that are here in the actual webinar, there's a chat enabled. So you'll see at the bottom, you can go ahead and click chat down there. You can type anything. One of the things we would like to do for questions, and if you've got a question for the panelists, we'd like the questions to all come into our Discord. And so that way they'll be saved and you can reference them afterwards as well. We'll try and give a good answer there. And we'll also try to answer, the panelists will answer for you here. So in just a moment, I'll share a link to the Discord channel. It's a Bayesian Discord server. And there's a thread there where you can put any questions that you have here. And we'll make sure those questions get to the panelists here in today's session. Of course, you feel free to use the chat that's in Zoom there as well, and you can send a message directly. I'll be using the chat to share some links, and of course to share the info to Discord as soon as I shut my app here in just a moment. Two other quick things. For those folks that are in attendance that have registered here for the webinar, you'll get our newsletter that comes with a bunch of great content such as this. You'll also be able to take advantage of a free consultation if the things that we talk about here today, optimizing over uncertainty to make robust decisions here. If that's something that interests you, is useful to your line of work, I would like to offer you a free consultation of 30 minutes. And so you can just reach out and we'll take advantage of that. I'm happy to learn about your use case and offer some tips and maybe how you can apply this into your world. So hopefully this sparks some interest and you can take advantage of that consultation following the webinar. And so with that, I would like to hand it over to our two panelists today. We've got Jay Laramore, who is a product marketing director at FICO Xpress. And we've got Dr. Daniel Saunders, who's a principal data scientist at PyMC Labs. Gentlemen, thanks so much for joining us today. Looking forward to the content here. And if we've got any pressing questions, then I'll just hop off mute and go ahead and ask them to you. But gentlemen, the floor is yours.
Awesome. Thank you so much, Evan. Well, welcome, guys. The title of this talk is Stop Optimizing Point Forecasts. We're going to look at robust decision modeling with PyMC and FICO Xpress. Daniel, if you don't mind advancing to the next slide, we'll go ahead and jump in. But before we propose any real new methodology, if you will, I always like to say, why not point forecasts? And the reality is, if we were to take a stochastic time series and try to say, in the next 2 weeks, we can say with certainty what those forecasts are going to be, decision makers would be a bit skeptical of that. They inherently know, you inherently know, we all inherently know that there's uncertainty present in those decisions. And they know that there's rarely, if ever, one optimal solution to their supply chain problem. And then point two is that, risk and uncertainty, when we're looking to control for risk and control for those worst case scenarios and try to mitigate those, that risk and uncertainty lives in the tails of the distribution. And point forecasts, especially expected value or mean forecasts, ignore those tails entirely. And there's a quote from the economist Thomas Sowell where he says, there are no solutions, only trade-offs. And so I invite you, as we go through these slides in the next hour or two, think in terms of trade-offs and not solutions. So if not point forecasts, then what? We're going to look at two approaches today from an optimization standpoint. And we'll talk more about FICO Xpress and mathematical optimization in a moment. But the first approach is going to be making decisions some user-defined percentage of the time across all plausible forecast scenarios. We're not going to look at one single point estimate across time. We're going to look at, in fact, a probability distribution of forecasts across that future unobserved period. And we're going to take that and taking a user-defined percentage, we're going to focus on a user-defined percentage across those to really focus on that tail risk. And you'll notice what this first approach does is it focuses on the frequency of demand shortfalls, assuming that we're forecasting demand. It focuses on the frequency of those demand shortfalls. And really the question that this is helping to answer for us is, based on all plausible future demand scenarios, how often am I willing to allow production to fall short of demand? We can set that user-defined percentile to be as risk averse as we want to. We can set that to be 99%, 98% if we're very risk averse, or we can set that to, again, any user-defined percentage that we choose to. But one thing you'll notice is that first approach doesn't account for the severity of the misses. It's very much a frequency-based approach. The second approach we're going to talk about is going to make decisions that control for the severity of losses in the most extreme but plausible scenarios. And so we'll unpack these differences as we go forth in the slides. But the question that this second approach is going to answer for us is, based on all plausible future demand scenarios, if and when production falls short of demand, how severe am I willing for those shortfalls to be? And so two similar but different questions that we're going to use mathematical optimization to unpack as we go forward. So kind of a quick summary of where we're going. We're going to take a very simple use case that we invite you to take, access from the GitHub page, and then really to kind of build out the complexity for your own specific use cases. But those two approaches, the frequency-based approach is called a chance constrained optimization model. And again, the goal of that chance constrained model, that frequency-based approach, is to minimize total cost while meeting demand some user-defined percentage of the time across all plausible forecast scenarios. That severity-based approach is called Conditional Value-at-Risk, or CVaR for short. And again, that's going to focus on the severity by minimizing total cost while controlling for the severity of those losses in the most extreme but plausible scenarios. One thing underlying both of these approaches are probabilistic forecasts, and that's where PyMC comes in extremely critical, because each of these are going to use probabilistic forecasting distributions to help estimate all plausible future outcomes. So the example we're going to look at today is from the energy sector. Although I think as we go through this, you'll realize that this methodology can be applied across any industry, from a supply chain and a forecasting-based type of problem. But we have historical, just a univariate time series with Ontario's daily energy demand. And we can probably see a little bit of trend, certainly some seasonality. We can diagnose and decompose the systematic or signal components of this time series and extrapolate forward into the future. But the question we're trying to answer with this historical demand time series is, how much energy will we need in the next 6 months for just a typical type of energy demand planning problem? And so you'll notice these are on the daily interval. So daily forecasts across 6 months is a ballpark of around 180 future forecast periods that we'll need to generate with PyMC. You'll notice a forecast is not a decision. Where the decision comes in and where the optimization component of this problem comes in is, we have a broader business objective that we're trying to answer, and that's to determine how much electricity from each one of these 5 sources, how much of the electricity to generate daily across that 181-day planning horizon. You'll see we have 5 sources: nuclear, hydro, gas, wind, and solar. We have some input data for each one of those. So we have the availability, which effectively serves as an upper bound in the optimization model. So how much available per day for each source. We have a cost parameter, which serves as basically a marginal cost for how much does it cost for each additional megawatt hour of of each source to produce. And then lastly is kind of an indicator column indicating whether or not this is considered a clean energy source. Because you'll see the second bullet point down below, one of the business requirements that we have to make is observing an 80% total electricity generation that comes from clean sources. And so we'll need to make sure that we build that out in the optimization model that we build. And so here I will turn it to Daniel to start us off with the forecasting methodology and how PyMC is used to build those probabilistic forecasts.
Hey everyone. So for the rest of the talk, we'll focus on providing an explanation about the main forecasting model and how we generate uncertain forecasts. That'll be kind of my section, and then I'll turn it back to Jay to talk about how does the optimization problem really work at the software and mathematical level. So there's lots of forecasting techniques out there in the world, and they can provide you something, most of them provide you something that would look kind of like this. You get a single prediction for each day about expected energy demand, and then you can incorporate whatever kind of model structure that you're interested in, such as here we have a bi-yearly seasonal effect, a trend, and then a weekly effect as well. And if you have a forecast like this, it's okay for answering some kinds of questions, but it's going to be insufficient for answering other ones. For example, if your goal is to meet demand 99.8% of the time, then knowing what the expected electricity demand in the future is going to be isn't terribly helpful to that goal, because it doesn't tell you what are the tail risks, what is the potential surge in demand that goes above your expected value. And in many contexts, this is really important. Energy generation has standards that suggest that you can only have one blackout every 1,000 days, for example. So if you need to meet regulatory requirements, they can often take the form of a chance constraint. The other case where this is insufficient is where underproducing is worse than overproducing, or vice versa. If overproducing and underproducing are kind of roughly symmetrical, then you can make the case that just looking at a single point would be adequate. But if there's kind of asymmetry in how these different outcomes affect your business or some kind of welfare metric, then you really do need to know the shape of the distribution around this point. Bayesian methods will give you a full probability distribution. So what I've plotted here is the historical reconstruction of the data according to the model, and then also the forecast for the future with different kinds of uncertainty bands highlighted. So you get the mean prediction, but you also get the 50% interval, the 90% interval, and so on, and it gets progressively more transparent. And when you have a distribution like this, you can answer those questions. You can ask something like, what's the probability that demand is 500,000 megawatt hours or more? You'll see, I think my cursor appears on the screen. You'll see that the upper y-axis is 500,000 megawatts, and there's a few days where it's possible that there's really high demand, and we've realized that demand in the past historically. So this is kind of an interesting problem for planners, is how often do I need to be able to reach that kind of surge capacity? And you can also take any kind of proposed energy generation plan and measure what are the range of possible outcomes and how good or bad are those going to be in a quantitative way. I imagine our audience has some familiarity with PyMC, so I want to spend most of our time letting you learn about the powerful solver in FICO. But I'll take you through kind of the basic structure of the model that I just showed you, and maybe some ideas for how you could improve that model in a more realistic context. We picked a really simple model because we want to just focus on this question about how does uncertainty translate into decision-making, not that this is the most powerful forecasting model you could build for electrical demand. So our model has a few components. It has an intercept, the kind of base level demand. It has this bi-yearly seasonal component, which represents the idea that the summer and winter you need more electricity than you do in the spring and fall. As well as this weekly component, which represents the idea that maybe weekends or Friday nights are especially they have especially high energy demand because people stay out later than they do otherwise. So maybe there's some kind of weekly pattern to be captured there. Or the reverse, maybe people don't go to work on the weekend, so the factories and offices use less power in those cases. And finally, there's a trend. The population of Ontario is growing. Climate change is putting more strain on their energy generation. So there's a long-term trend to capture as well. With Bayesian models, all parameters get prior distributions. So we go from a probability distribution over all parameters, and we train on the data, and we get a new probability distribution over all parameters. So this is the syntax to express the idea that the variance around the prediction should be constrained in this particular way. And finally, the kind of most interesting component for us is the likelihood. This expresses assumptions about how errors are likely to be distributed around the expected value. So the classic distribution is the normal distribution, which suggests that they're symmetrical and additive around the expected value. But I think in the electricity demand case, a log normal is a much more compelling choice. And the idea is that the log normal is asymmetrical and has long tails. So it encodes the assumption that there can be really extreme spikes in demand, and that they're going to be more extreme than you'd get under other distributions. And these things are asymmetrical. When like an unexpected natural disaster or bad thing happens in our world, it's rare that the result is you need way less electricity. Usually you need way more. So because of that asymmetry and how errors tend to be distributed, the log normals are a really natural way of expressing that. Once you have a model, PyMC is a library built around the idea that you want to sample from probability distributions. So earlier, Jay was talking about taking multiple projected scenarios for the future and analyzing them to create an optimization problem. The sampling is the engine that gives you a distribution of scenarios. So at the end of the day, you'll end up with 4,000 predictions for what might happen in the future. And the kind of frequency of those predictions represents their probability. So you'll get more predictions closer to the expected value and fewer further away. And the way we do this is we generate a custom Monte Carlo Markov chain that can sample from an arbitrary probability distribution by analyzing the structure of the program that I showed you below. And the kind of state-of-the-art technique, the one that's very fast and very scalable, is the Hamiltonian Monte Carlo, which I'm displaying here on the screen. And it uses the kind of gradient information of the shape of this probability distribution, this kind of enormous joint distribution over all parameters that you're estimating. And it tries to smoothly glide around in that space. And it'll run for a little bit, we'll stop it, we'll collect a sample, we'll turn the trajectory around and run it for a little bit longer and collect another sample. Now, I mentioned that the model is very simple, and that the main goal here is to talk about how do you make decisions on the basis of it. But they do want to just mention that PyMC is a very flexible library, and you can take it as far as you want to. So you can write arbitrarily complex model structures. There's even this idea known as a Gaussian process, which is a probability distribution not over parameters, but over functions. The idea is, I don't know if there's 2 seasonal terms or 3 seasonal terms. I don't know if the seasonal terms repeat exactly every year, or if there's some slight drift in how that seasonal function changes over time. A Gaussian process is a way of, you don't make decisions over those particular details, you make decisions over types of functions that could generate the prediction. And I borrowed this from a colleague who created a demand forecast of electricity in Great Britain from over a 5-year period. And you can see that the seasonal component is rather irregular. It doesn't repeat exactly over time. And it has kind of more bumps and turns in it than you would get with just an ordinary, adding multiple 4-year terms to your model over time. So that's just my plug to say that if this model doesn't strike your fancy, you could build one that would. And in the end, you still get the same probabilistic forecast of the future, which can be consumed by FICO. So I'll turn it back over to Jay to give us the last half of this talk.
Awesome. Thank you, Daniel. So going through this example, we've used PyMC to generate probability forecasts for the next 181 days inside of PyMC and inside of Python. The next step is to bring in the FICO Xpress Python API to connect that workflow end to end. You guys are probably very familiar with bringing in different Python packages. At Xpress is no different. We can just simply import Xpress as XP, import all of your other favorite packages into a broader Python workflow. Xpress also has other APIs. So for the non-Python programmers, we have APIs into C, C++, Java, .NET, R, MATLAB, so on and so forth. Suffice it to say, whatever programming language that you have, you'd be hard-pressed to find an API that we don't have access to in terms of building and solving those optimization models. But we're going to stick exclusively with the Python API for this demo. In addition to the FICO Xpress Python API, we have a handful of other technology products that we use to build, solve, and deploy optimization models into production. The first column, everything revolves around our set of solvers. And so if those acronyms in the solver category are unfamiliar to you, depending on how you formulate your optimization model, whether you have binary or integer decision variables, whether you have a quadratic objective or a quadratic constraint, whether you have non-convexity, so nonlinear, non-convex objective functions, where you want to find the global optimum value, not just arrive at some local optima. We have a variety of different solvers that you can pick and choose to solve your model based on how it's formulated inside of Xpress. We're going to focus primarily, the two examples that we're going to run today are very simple. So they'll be linear programming models, but natural extensions to these would include mixed integer programming, mixed integer quadratic programming, and perhaps even global mixed integer nonlinear programming for any types of non-convexities that exist in our model. I won't go through all the list here, just for sake of time, but the product directly next to Xpress Solver is Xpress Insight. And this is our interactive visualization environment that allows us to deploy an optimization model in Python through Insight to build dynamic dashboards and run various types of scenario analyses. So the way I like to position Insight is this is what executives see when we're making the business use case to deploy in that business environment. They're never going to see the code. They're never going to learn about the complexities necessarily of the model, but they're going to see the results. They'll see the charts, and they'll see the insights coming from the optimization model. Let's jump into that first example, the first chance constrained model I mentioned earlier that focuses on the frequency. And you'll see we're going to build inside of the FICO Xpress Python API 3 sets. First is just a set of all power generation sources, the 5 that we saw earlier. The second is going to be a subset of only those clean power generation sources, which I believe were 4 out of the 5, with the exception of gas. What you'll see highlighted in yellow are where the PyMC forecasts are going to come into the optimization model. So you'll see the set we're calling T. That's the set of days in the planning horizon, which in this example is 181. Down below, we're going to read in parameters, which is our known input data into the optimization model. And you'll see that the various notations, we're going to read in that cost column that we saw earlier. We're going to read in the availability of each source, which will serve as an upper bound for each day in the model that we build here momentarily. We're defining theta as that clean energy target. If you recall from the slides earlier, there was a business rule that we have to accommodate saying that at least 80% of the power generated each day must come from a clean energy source. And so we're using theta here to represent 80%. Where the PyMC forecasts come in is in this d sub t beta parameter. And notice this is for each t in our set of 181 indexed set of equally spaced observations. And again, B here, this is the Bth percentile. So this is user defined. We're going to use 95% in this example, but again, this is subject to the researcher's discretion of what percentile to use. And we're going to read these in directly from PyMC. One thing to point your attention to before we go forward is that we're running several thousand scenarios, forecast scenarios each day across the 181-day time period. And that's going to result in hundreds of thousands of different points. But for this parameter, we're only going to extract the 95th percentile value for each day. So d sub t beta effectively corresponds to a 181 by 1 vector of 95th percentile demands for each day in that planning horizon. Our decision variables, in short, these are the things we want to find the optimal values of. And so here, this is going to be the electricity generated each day for each source during that planning horizon. So you'll notice that we're denoting these decision variables as x sub st for each one of our sources across each one of the 181 days. And we're denoting those decision variables x. Our objective function is going to be to minimize total cost. So summing across all our sources across all 181 time periods, the optimization model behind the scenes is going to find the optimal decision variable values that minimize this function here. And you'll notice this is just a linear objective function where we're multiplying the optimal decision variable values by their respective marginal cost for producing one more unit of each source. So we've talked about sets, parameters, the decision variables, the things we want to find optimal values of. One thing to mention about those decision variables, those are also allowed to be continuous. In FICO Xpress, we're also allowed to have integer decision variables as well as binary decision variables. So it's not uncommon to have a model where we want to, do we add this facility, yes or no? And so we can incorporate various types of decision variables into optimization models. But for this example, we're allowing those to be continuous. For the chance constrained, or rather for the demand satisfaction constraint, here's where we're reading in that 181 by 1 vector of 95th percentiles. This essentially is saying that for each one of our time periods, planned generation must be at least as large as the Bth percentile forecasted each day. Looking below at the Python Express API code for how to get those from PyMC into Express to declare and define that constraint, it's only 2 lines of code. We're going to create a variable here, demand underscore 95th, which is going to extract that 181 by 1 vector from the output from PyMC. And then down below, building that constraint into FICO Xpress, we're going to use the prob.add constraint function to build out that constraint that you see on the screen. Could you go to the next slide, please?
This is the clean energy one.
Oh, you beat me to it. You're right.
Yeah.
Okay, thank you. Last but not least, this doesn't have anything to do with PyMC itself, but I just want to kind of illustrate how we can build constraints very much as business rules in FICO Xpress. And I'll give you guys a few additional examples outside of this use case in just a moment. But here, this clean energy constraint just ensures that at least 80% of the amount of energy produced each day comes from one of those 4 clean energy sources. And so we can declare and define that. And down below, you'll see inside of Python or inside of the FICO Xpress Python API, how we can formally write that inside of Python. We were talking before this webinar kicked off about different types of price optimization examples and how Bayesian can be incorporated with deterministic optimization like FICO Xpress to build price optimization models. And so some additional examples of constraints that you may come across, one that I came across recently were called price laddering constraints, where we want to find the optimal prices, and those being our decision variables, but we want to constrain those price ladders. So for example, if we're in a fast food restaurant and we're doing price optimization for a fast food restaurant, we might want to constrain those prices, saying that the price of a double cheeseburger can't be less than the price of a cheeseburger, right? And so we can build in those business rules and constraints as we need to inside of our optimization model to meet and satisfy any business requirements, regulations, or SLAs that we might have. So running that chance constrained model, again, we chose 95% to be our user-defined percentile. And notice that's represented by the red lines there. And this works very well. It's a very simple model. But I want to point out what it doesn't account for. So notice, and Daniel pointed this out earlier, that there are a few cases where demand exceeds the amount produced. And we can kind of flag these here on the screen. What this model does not account for is the severity of those misses. And so this next model, the conditional value-at-risk, focuses on minimizing the severity of those shortages if and when they occur. This is a much more risk-averse model for situations where it costs a lot of money or it's very detrimental for any shortages to exist.
Sorry, got frozen a second. Okay.
Oh, you're fine.
Yep.
The good news, the CVaR model is just a simple extension to the chance constraint model. So everything we just saw from the chance constraint model is applicable in the CVaR model. And so we're just going to look at what are we adding to this new CVaR model in FICO Xpress to account for the severity. And the first piece is a new set we're calling Omega. And this is the set of all forecast demand scenarios generated by PyMC. So if you recall from the chance constraint model, we just cherry picked that 95th percent vector, that 181 by 1 vector. Here we're reading in every single forecast demand scenario. And so you can do the math, 4,000 per day over 181 days. This is going to be a much larger model with a lot more input data that we're reading into it. As a result, and again, this is subject to the user or to the researcher's discretion, but it's not uncommon to choose a representative sample of demand forecasts or of demand scenarios, especially as that number gets larger and larger. A few new parameters that we're adding in, and we'll talk about each of these as we go, but the one that incorporates these scenarios from PyMC, we're removing the d sub t beta. So we're removing that 181 by 1 vector and replacing it with d sub omega t. So we're reading in every scenario across all time periods. And you'll see down below, we put the math down there. So 4,000 posterior samples per day across a 181-day planning horizon equals not 181 like the chance constraint model, but 724,000 d sub omega t parameters. So we're reading all of them in. Down below, 3 new parameters that we're going to add in, and these might make more sense as we talk about the objective function and some of the constraints. But P is going to be a penalty cost per megawatt hour of unmet demand. This value is user defined, but often we want to set P to be a value that exceeds the largest cost from any one of our sources. So from memory, I believe the largest cost or the largest marginal cost was $85. So we would want to set P to be a value greater than $85, so the model's penalized more for not meeting demand. Down below, the alpha, this is the tail probability of the shortage loss distribution that we'll calculate with CVaR. And I'm arbitrarily choosing to define alpha to be 0.05. What this means is that meaning that this CVaR term is going to measure the average shortest cost across the most extreme 5% of scenarios in the shortage loss distribution. So we'll be focusing on minimizing the most extreme tail risk from that shortage cost distribution. Last but not least is lambda. This will make more sense once we see the objective function, but this is the weight that's placed on the conditional value at risk in the objective function. And so this is user defined. I'll talk a little bit more about that once we get to the objective function portion. I think it'll make a bit more sense then. We're going to add several more decision variables. And again, decision variables, these are the things that the optimization solvers are going to find the optimal values of. And for each scenario across each time point, so 724,000, I believe it was, we're going to have a variable for each demand scenario indicating whether unmet electricity demand, indicating whether there was any unmet electricity demand in each scenario for each day. We're going to also introduce a variable called Z, which is going to represent the value at risk threshold. And what this does is this, along that shortage loss distribution, this value is going to separate what we consider ordinary shortage cost outcomes from the most extreme shortage cost outcomes. And so again, it's those most extreme that we're going to focus on, and its value of Z is going to determine where on that shortage loss distribution is effectively the lower bound for those most extreme. And last but not least, we're going to create an auxiliary variable for each scenario, and this is the amount of shortage cost in each scenario that exceeds the VAR threshold, right? So any scenario where the auxiliary variable is greater than 0, that's what we're going to look to minimize in the objective function. You'll see down below in the FICO Xpress API how easy it is to declare and add decision variables. We're given the option to use the add variable function, give it a name, give it a lower bound if one exists, give it an upper bound if one exists, and then very simple and straightforward inside of FICO Xpress to declare these decision variables. Here's the objective function that I talked about a second ago, and you'll notice that it's just an extension of the chance constraint objective. The chance constraint objective was simply just to minimize cost. And we still have cost as part of our objective function, but we also have introduced this new CVaR risk penalty. And essentially what this CVaR model is going to allow us to do is to look at various scenarios to see if we want to effectively buy certainty, how much is that going to cost us? These two values are competing objectives in a sense. That if we want less risk, that's going to be more expensive. If we're happy with more risk, then we can perhaps get a lower cost. What lambda does is it's a weight on the second part of this objective for how much are we weighting the CVaR risk penalty. And so for this particular model, it's not we typically don't run this once. In fact, we'll run this model for various lambda values to take a look at the trade-offs between the CVaR risk penalty and the total cost. And in the next several slides, you'll see an example of a Pareto frontier where we look at the optimal trade-offs across these two. Taking a look at a few new constraints that we'll define in this model, this shortage constraint replaces the demand satisfaction constraint from the chance constraint model. And this is effectively defining shortage as the amount of demand that exceeds the planned generation. So if you'll recall earlier, when we declared this decision variable, we set a lower bound of 0 for it. So if demand for a particular scenario at a particular time point exceeds its planned supply, then that shortage value will be greater than 0. If supply exceeds demand, then that will be a negative number, but the lower bound that we set on that decision variable will force this shortage value to equal 0. And so this was one of the linearization techniques. In fact, this CVaR model methodology is called the Rockefeller-Urashev model. And what they did was to effectively linearize a nonlinear model. So it was more scalable and much more robust. And so shortage will effectively be the max of either 0 or the difference between demand and supply across the different scenarios and time points. But it's a shortage decision variable that's going to be used to construct that shortage loss distribution. And it'll most likely be 0 inflated, but it's the alpha fraction of this shortage loss distribution of those tail scenarios that are penalized in the objective function that we just saw. So I mentioned earlier, both of the formulations we just saw for the chance constrained model and for the CVaR model were formulated as linear programs using the linear programming solver. And these were very much simplified, primarily just to show the mechanics of how each works. And Daniel, Evan, and I, we wrote a blog that we'll put in the chat that goes into these model methodologies in a little bit more detail. So if you want to take a look at those parameters in more detail and kind of learn how each one works, the goal was to take that and adapt it to build out more complex supply chain type of models. Because in reality, it's not uncommon for a CVaR model or a chance constraint model to have binary unit commitment decisions or startup and shutdown costs, right? Do we start up this plant? Do we not? And so that introduces us into, mixed integer programming as well. And if we have quadratic or nonlinear constraints, perhaps even mixed integer quadratic programming or mixed integer quadratically constrained programming. And so the point is not to unpack all the complexity here, but just to show you that if and when your supply chain model becomes more complex, FICO Xpress has every solver available to help solve those more complex problems. Ramping limits are very common if you have certain reserve requirements, minimum up or down times, whatever the case may be. If formulated using the FICO Xpress API, we have the appropriate solver for you to be able to solve and call that under the hood to be able to address any of those additional complexities. Let's take a look at the examples or the results from the two simple linear programming examples that we just ran. So I mentioned earlier that the CVaR model is a bit more conservative, a more risk-averse model. And looking at the results, running the two side by side, the CVaR model recommends generating about 8.5% more electricity on average. And that's going to increase cost as well, right? We want to buy certainty effectively. We want to be a little bit more risk averse at the result of increasing cost by about 22%. But that's going to reduce our shortage rate from 5% down to 0.35%. And you can take a look at the chart on the right-hand side of your screen. The chance constrained model is looking at an average generation of about 461 gigawatt hours per day, whereas the CVaR model is generating about 500 gigawatt hours per day. We can take a look at the total cost. CVaR is a bit more expensive, but has a much lower shortage risk. And kind of going back to the Thomas Sowell quote I mentioned earlier, they're really with these, there are no solutions. They're really only trade-offs. So looking at how much shortage risk are we comfortable with, and at what cost are we comfortable with? I mentioned in the objective function earlier about lambda. It's not uncommon to run CVaR numerous times. And in fact, in this example, we ran that CVaR model 1,000 times and generated what's called a Pareto frontier. So if you take a look at the y-axis, this is our planned generation cost. So that was the first part of the objective. And the shortage rate corresponded to the second part of that objective. And in a perfect world, we would be is if both of those were 0, 0. So anything to the bottom left of this red Pareto frontier is an inefficient solution. It just doesn't exist. It is impossible. Everything to the top right of that red Pareto frontier is considered Pareto inefficient. And what that means is if we have a current Pareto inefficient solution, we can reallocate our decision variables to fall somewhere along this Pareto frontier to look at what's called making a Pareto improvement, to fall somewhere along this Pareto frontier and then look at the different trade-offs, based on if we want a lower shortage risk. And we can see how cost rises as the shortage risk approaches 0. Or if we're comfortable with a larger shortage risk, we can see what type of cost savings there are. But this is typically one of the presentation graphics that I mentioned inside of Express Insight that we commonly show to executives and to business leaders to take a look at the various trade-offs that exist in this type of environment. You might notice as well the blue Pareto frontier. So we had some fun. We went back to that clean energy constraint and we said, well, what if instead of that theta value being 80%, requiring 80% of all values or all energy produced each day to be clean, what if that was raised to 90%? How would that impact the shortage rate? How would that impact the cost? And so we took a look and ran some scenarios to generate that Pareto frontier as well. I'll close with a few additional resources. Again, we wrote a full blog that goes into this in much more detail. So I invite you, if you're curious or interested about how this can be applied to your supply chain problems or to your industry, please take a look at that blog. And if you want to run this exact scenario and kind of get into the Python code and play around with it yourself, we have a GitHub link directly below that will take you to that stochastic energy planning problem and allow you to run those scenarios, change theta, change P, and kind of make it your own and kind of learn by doing in that sense. We have a few more. Yep, and we just have a few more getting started examples with Python Express. So if you're curious, what other types of problems can optimization and Python Express solve? We have a whole notebook with different examples just to kind of learn the art of the possible.
Thanks so much, Jay, and thanks, Daniel. We've got, I don't think anything is clickable on here, but I did just leave the blog link in the webinar chat, so feel free to click that, and all of these resources are clickable there from the blog, including the code. We do have about 10 minutes remaining for questions. Daniel and Jay have been kind enough to offer to hang on for a little bit and answer a few questions. So if you've got questions, please feel free, go ahead and put them in the chat here. I left the link for Discord if you want to join the Discord so you can continue conversation after this and leave your questions there as well. Jay, I think this probably first one for you came in from LinkedIn. Does the solver account for uncertainty in costs, value parameters, other parameters in the decision framework in addition to uncertainty for the demand model parameters? Could you
Yeah,
develop something in architecture that accounts for uncertainty across other parameters as well?
yeah. So it absolutely can. We started with a simple example that just accounts for uncertainty in one place, right? But there's no reason that if you have uncertainty in kind of multiple facets, that can't be constructed and taken into the objective function to penalize that as well. What we showcased was an example of a two-dimensional Pareto frontier where we had just an X and Y axis. It's not uncommon in real world scenarios to have kind of a third penalty or a fourth penalty and really get into that kind of three-dimensional or even four-dimensional Pareto frontier, which is a little bit less, a little bit more difficult to visualize, but conceptually it works the exact same way.
Perfect. Yeah, and I think starting with the example there is great. And then maybe Daniel, the example on the forecast came out. We're sort of forecasting one single parameter, the demand likelihood. But it can PyMC also, if there's a forecast that's across maybe multiple regions or there's multiple facets, can PyMC handle things like that are more than just sort of a singular value that are trying to forecast?
Yeah. So like in the cost case, you could also just have a forecast of the cost over time. And then you'll have to have some strategy for analyzing what you're going to do with those probabilities. So you might take the expected value of the cost over time and hand that to FICO, or you might do something kind of like worst case, best case, where you take upper and lower bounds, or an even more rich kind of like full probability distribution, kind of like some kind of utility function to incorporate the whole probability distribution into the cost that you hand off to FICO.
Great. Thank you. Again, I'll invite others to share questions. I've got a few here that people have shared with us, but if you want to post in the chat or join us on Discord there, then we welcome any questions. Um, I maybe a question, I'm not sure who this question is for, but you mentioned, Daniel, in the forecast the likelihood function, the log normal likelihood function. How sensitive would you imagine the optimizer is to the function that you use, and sort of like a log likelihood with sort of the longer tail? Would this change materially the way the optimizer runs, if you choose a different likelihood function?
Yeah, it would. So because both of these two optimization strategies are really sensitive to the structure of the tail, the normal distribution just has a shorter tail on the upper side. So you're going to get a situation where the 95th percentile is lower. So then your plan will be cheaper. And if you're wrong about that assumption, you're more vulnerable to surges in demand. You similarly with the chance constraint, you also need to have a kind of full picture about what that upper tail looks like. So being wrong about the distribution choice can have bad effects on how you handle the tail via CVaR as well.
So thank you. Jay, I think this question probably for you, Jay, but Daniel, feel free to hop in as well if you've got comments. What what do you so we're sold. This is great. This is the way forward. We should stop optimizing with point estimates. But here's the thing: we've been optimizing with point estimates, and we've got a forecast or a predictive model, and we're using a single point estimate. And how do we go from that to more robust decision making, where we're including that? And sort of how do you make the case for folks to try to sort of add this complexity and showcase that it's worth it? I think you've done so in the webinar here,
Yeah.
but if you've got sort of an elevator pitch for yeah, sure, you've got this now, but why do we need something that's going to add some complexity?
Yeah, and that was my life too. Before I was using point estimates, right? So pick your favorite ARIMA model or state space model, and I built them using point estimates, and I've fed into optimization models in the past. one thing that I personally had trouble with is I could never convince decision makers that this was actually going to be robust in the real world. And so I had to learn really by trial and error, because the questions they would come back with me at, I couldn't answer in a point forecast methodology. The few times I put those into production, they would work okay under normal circumstances. But the second anything atypical happened, they would crash and burn. And so from a trust and reliability, and I'll give you a great example. Before about 10 years ago, I used to work at a retail fuel gas station. And so we owned and operated 1,500 retail gas stations in the southeastern part of the United States. And we would forecast daily fuel demand for each one of those, unleaded, mid, premium. And we would try to control for the spikes and minimize residual variance as best we could. But inadvertently, there would always be something at one of the stores where traffic got diverted, and so that drastically reduced demand. I mean, things that we couldn't possibly predict, but just real world situations that mean forecasts just never were robust. And so the issue we had was getting the field to trust us and get the field to buy into point forecasts. And so it had intermittent success, but kind of my pitch, if you will, the probabilistic, getting that full probabilistic distribution allows you to, much better tailor and craft how you associate with that risk and uncertainty.
Got it. Yeah, spot on. And I think, unfortunately, oftentimes that's probably a lot of the ways you get to push people into a more robust methodology is wait for the more fragile methodology to fail. And when it does, they'll want to use it. Great. We are just about at time. Jay, Daniel, thanks so much for joining on, for sharing. I've dropped a couple more resources in the chat here. It's the blog post and the Discord server again, and then a reminder for anybody who is in attendance today. If this problem is near and dear to your heart, then we'd love to offer a free consultation. We can hop on a quick call and point you in the right direction for how you can use the tools that we talked about today in your specific use case. So thanks very much for joining, everyone. Jay, Daniel, thanks for the great content.
Thank you, guys.